So you should have received test 1 back in your email. If you're looking at the test and you can't see the grading on it, the inking on it, it is inked right in Word. So if you can't see it, try to open it on a WITC computer. You should be able to see it. If you still cannot see the inking on the test, let me know and I can try to print it and rescan it as a PDF and send it to you that way. But just a little bit of a quick summary on test 1. As I was going through test 1, I found 2 questions that I decided were unfair. So I eliminated those 2 questions. And the way I did that is in the grade book, you'll see there's the test 1 grade. There's test 1 review for extra credit. You still can work on that till the end of the day today, by the way. And then I put in a test 1 correction. And with that test 1 correction is just everybody, I put in 7 points for that. That is the points. The point value is actually 6.7, but I rounded up to 7. That's the point value of the 2 questions that I decided were not really fair to ask. Giving you a graph that doesn't cross the x-axis, has no real roots, was kind of mean of me. That was just my fault of not checking my work close enough. I misprinted it. It was supposed to be a +8 and I put a +9, so that made it a whole different question. And there was another one on there that I decided wasn't fair. So what I did is I didn't eliminate those questions off the test because some of you still had those questions right. So I didn't want to take away your points for getting them right. So I just added 7 points in that way to everybody's score. Now with that said, you still have your other test scores. You can still redo the problems you got wrong on that test. So let's say you had an 80 out of 100 on the test. If you redo the problems you got wrong, probably on a separate sheet of paper or whatever, and scan them and send them to me, I will give you half your points back. Now you do have to show all your work and all your steps when you redo them. So that 80 would be +10 back to 90 out of 100 very quickly. So please take a look at doing that on the problems you got wrong. Is there anybody that did not get their test back yet? Okay, perfect. Like I said, if you can't see the markings for the gradings, open it on a WITC computer, and if you don't have the correct version of Word, sometimes you can't see them. Okay, well today we get to start Unit 2. And in Unit 2, we're starting in sections 3.6 and 3.7 of the textbook. And we're looking at going the next step. We've talked about these polynomial functions and rational functions and graphing them. Well, now we're going to look at polynomial and rational inequalities. So remember, an equality simply has one of these 4 symbols in it instead of an equal sign. So we're not finding individual solutions, we're finding ranges of solutions. So an example of a polynomial inequality might be x squared minus 4x plus 3 is greater than 0. So it's a polynomial, it's not linear because it's got a power greater than 1 on the variable. To solve it, the first thing we want to do is we want to find, well, obviously the first thing we want to do, this one's already has it done, is to set it equal to 0. Well, this is already not necessarily equal to 0, but it's being compared to 0. So it's not equal, but it's greater than 0. The reason for that is that allows us then to use our 2-dimensional graph, and the x-axis is going to be where the value is 0. Second step then for a polynomial inequality is to find the roots. So to find roots, it has to be equal to 0 or compared to 0 like this one is. And then we're going to factor. And technically what I can do is I can put in an equal sign here while I'm working with it, because that's the way I'm going to treat it here. Well, x minus 4, or x squared minus 4x plus 3 is x minus 3 times x minus 1. Which gives us, if I'm using the idea of equal to 0 here, gives us that x minus 3 equals 0 or x minus 1 equals 0. Now we've worked with these enough to know I'm not going to do the adding here, but this gives us x equals 3 or x equals 1. Those are roots. And what I'm going to do is I'm going to plot them on an xy graph. So there's x equals 1 and x equals 3. Those are the roots. So what this does is it divides, if I'm looking simply at the number line for right now, the x-axis, it divides that x-axis into 3 regions. This region down below the -1, or below the +1, the region between the 1 and the 3, and then the region above the 3. So I need to know where it's greater than 0 and where it's less than 0. So I can just pick a test point from any of those regions. Actually, I could probably pick 0 would be easiest. 0, x equals 0, is in this first region down here, that's below 1. So if I put 0 into this, 0 squared minus 4 times 0 plus 3, well, 0 squared is 0, 4 times 0 is 0, well, 0 minus 0 plus 3 is 3. And that is greater than 0. It's true there. So it is true on this region. The center there between 1 and 3, well, the easiest value to pick there is probably going to be the 2. That's right between the 1 and 3. So let's try x equals 2 into this and see what we get. So 2 squared minus 4 times 2 plus 3. And we're checking to see if that is greater than 0. Well, 2 squared is 4 minus 4 times 2 is 8, and then plus 3. Well, 4 minus 8 is a -4, plus 3 is -1. -1 is not equal to 0, or not greater than 0. So it is not true in that middle range. On the upper range, larger than 3, well, let's pick 5. That's up in that upper range. So if we test out 5 in this inequality to see if it makes it true. So that'd be 5 squared minus 4 times 5 plus 3. Is that greater than 0? Well, 5 squared is 25 minus 4 times 5 is 20 plus 3. Well, 25 minus 20 is 5 plus 3 is 8. That is definitely greater than 0. So it is true on this region. We can express that then using 2 different types of notation. We could do set builder notation or solution set notation. Where we would say that this is true for all values of x such that x is less than 1 or x is greater than 3. Notice I use strictly less than and strictly greater than here because my original sign was strictly greater than. Or I could use my interval notation. If I use interval notation, I'm saying this goes from -infinity to 1. Now, what type of bracket do I put there? Square or round? Round. It's strictly less than, so it does not include the 1. And that is unioned with 3. That's also a round bracket because it's strictly greater than 3, not equal to, from 3 to +infinity. Now, I should note that there is a link between the graph of a polynomial function and the solutions of the polynomial inequality. This was x squared minus 4x plus 3 is greater than 0. If I were to graph the function f of x equals x squared minus 4x plus 3, its graph would look something like this. And from that graph, we can actually solve this inequality. Where is it less than 0 or greater than 0? Well, the graph is above the x-axis in this region and this region. So that's another possible way of solving these. If you like to graph them, you can just graph them out and see where the graph is above the x-axis or below it. Well, let's look at another example or two. We might have 2x squared plus 9x plus 7 is less than or equal to negative 3. Now remember, our first step is to get it compared to 0. Right now, there's a negative 3 on the right side. We can't have that. So to get rid of it, we're going to add 3. On the left side, the only place we can add 3 is to the 7 ones. So this now becomes 2x squared plus 9x plus 10 is less than or equal to 0. So now that we have that, we're going to treat it as an equation. Find those roots. So factoring this, obviously 2x squared is 2x and x. 10 is 5 and 2. And I'll leave it up to you to verify that we get the 9x for the middle term. We do. So that's saying either 2x plus 5 equals 0 or x plus 2 equals 0. Solving each of those, here we would subtract 5. 2x equals negative 5 or divide by 2. Got x equals a negative 2 1/2. Or over here you subtract 2, x equals a negative 2. So as we graph this, plotting those roots at least, give myself a little more space here. We have negative 2 1/2 and negative 2 are those roots. So I've got a point over here. This would be negative 3. In between them, we'll call that negative 2.25 or negative 2 1/4. And we use negative 1 for this region. So we're going to test them. I go back to the original inequality, just in case we did something incorrect as we were trying to set it compared to 0. So I've got 2x squared. I'm going to use the negative 3 first. So I'm going to test negative 3. So 2x squared is 2 times negative 3 squared. Plus 9x, that's going to be plus 9 times negative 3. Plus 7, is that less than or equal to negative 3? Again, I'm going to take a few shortcuts here. Negative 3 squared is 9 times 2 is 18. 9 times negative 3 is negative 27 plus 7. 18 plus negative 27 is negative 9 plus 7 is negative 2. Is that less than or equal to negative 3? No. So we do not appear to be true at the negative 3. Let's use the negative 2.25. So 2 times negative 2.25 squared plus 9 times negative 2.25 plus 7. We have to check to see if that is less than or equal to negative 3. Well, 2.25 squared and negative 2.25 squared is the same thing, is 5.0625 times 2 will be 10.125. 9 times a negative 2.25 squared is a negative 20.25, and then plus 7. 10.125 plus a negative 20.25 is a negative 10.125. Plus 7 is negative 3.125. That is less than or equal to negative 3, so it's true there. So we're true between the points, which means we're most likely not going to be true at negative 1, but let's test it anyway. So 2 times negative 1 squared plus 9 times negative 1 plus 7, is that less than or equal to 3, or negative 3? 1 squared, or negative 1 squared is 1 times 2 is 2. 9 times negative 1 is negative 9. 2 plus negative 9 plus 7 is 0, and that is not less than or equal to negative 3. So it's not true over there. So here our solutions are between negative 2.5 and negative 2, or negative 2.5 and negative 2. So we would write out that solution in solution set notation. In your notes, I want you to try to write out, for being between negative 2.5 and negative 2, write out the solution set notation, or set builder notation, and interval notation. I'll give you a second to get those jotted down. So since it's between these values in our solution set notation, we can set it up as a compound inequality. Negative 2.5 or negative 2.5, however you prefer to do it. Less than or equal to, because it was less than or equal to in the original problem, we have the or equal to there. X, which is less than or equal to negative 2. That is saying x has to be between negative 2.5 and negative 2. Interval notation, since it's or equal to, we do have square brackets, inclusive brackets. Negative 2.5 to negative 2, an inclusive bracket there as well. Any questions? Well, let's look at one that is the next step up. Not a power of 2, but a power of 3. So I have x to the third minus x squared minus 7x plus 9 is greater than 2. Now again, we have to set it compared to 0, so I want to get rid of that 2. I'm going to subtract 2 from both sides. It'll be gone, it'll be 0 on the right. The only place I can subtract it from is from the 9 ones on the left. So x to the third minus x squared minus 7x plus 7. And now we need to find the roots. We're going to treat this as x to the third minus x squared minus 7x plus 7 equals 0. And we're going to factor it. Finding the roots, the easiest way is to factor. This is 4 terms, so I'm going to try to group it. Remembering this negative has to go with that 7x. So x to the third and x squared is my greatest common factor, leaving me with x minus 1 inside there. Negative 7x and 7 have a common factor of 7. I'm going to take out a negative 7, so they get a positive x minus 1 inside that parentheses. Now I factor out the x minus 1. I've got x minus 1 times x squared minus 7 equals 0. Now this first factor gives us that x minus 1 equals 0, saying that x has to be equal to 1. That's one of the roots. The second one here is not imaginary, but it is going to be irrational. X squared minus 7 equals 0. We can't factor it, but we can break it down using that square root method. So we're going to add 7 to both sides to get the x squared by itself. X squared equals 7, and then we're going to square root it. So x equals the positive or negative square root of 7. Now let's approximate that on our calculator just so we know where to put it on our graph. That's about 2.65. So as I look at the graph of this, everything's positive. No, it's not. So there's my x-axis. I have the value of x equals 1, so that's a root right there. The negative square root of 7, so that's about negative 2.65, somewhere in there. And the positive square root of 7, so positive 2.65 is somewhere in there. So I have 4 regions that I need to test. Negative 3 is in this region. 0, if I can use 0 for anything, I always try to because it's really easy to use. 0 is between the negative square root of 7 and the positive 1. We'll use 2 here between the 1 and the positive square root of 7. And then 3 is above that. So we need to test each of those 3 to see where this is above or below the x-axis, whether it's greater than or less than 0. We want it to be greater than 0. So let's test the x equals negative 3. And again, I go back to the original inequality, just in case I made a mistake. So this is negative 3 to the third power minus negative 3 squared minus 7 times negative 3 plus 9, and we need to test to see if that is greater than 2. Well, negative 3 squared is a negative 27 minus negative 3 to the third is a negative 27 minus negative 3 squared is a positive 9. Now I'm going to do the negative 7 times negative 3 is a positive 21, and then plus 9. Is that greater than 2? Well, negative 27 minus 9 is negative 36, plus 21 is a negative 15, plus 9, that's still a negative 6. That is definitely not greater than 2. So we do not have solutions to the left side of that negative square root of 7. Let's test 0. I'll test it over here. This will be 0 to the third minus 0 squared minus 7 times 0 plus 9. Is that greater than 2? Well, yeah, everything here is zeros except for the 9, and 9 is definitely greater than 2. So there are solutions between the negative square root of 7 and the positive 1. Next, we're going to test the 2 here between the positive 1 and the positive square root of 7. So test x equals 2. That's going to be 2 to the third power minus 2 squared minus 7 times 2 plus 9. We're going to test to see if that is greater than 2. Well, 2 squared is 8. Or sorry, 2 to the third is 8. Minus 2 squared is 4. Minus 7 times 2 is 14 and plus 9. 8 minus 4 is 4. Minus 14 is negative 10. Plus 9 is a negative 1. That is not greater than 2. That region in between 1 and the square root of 7 is not a solution. So now let's test x equals positive 3. So 3 to the third power minus 3 squared minus 7 times 3 plus 9. Is that greater than 2? Well, 3 to the third power is 27 minus 3 squared is 9 minus 7 times 3 is 21 plus 9. 27 minus 9 is 18. Minus 21 is negative 3. Plus 9 is 6. That is, again, definitely greater than 2, so that is true. So the regions where this is true is between the negative square root of 7 and positive 1, and then greater than the positive square root of 7. So the solution set notation here is going to be a little tricky. It's all values of x such that x is between the negative square root of 7 and positive 1, or x is greater than the positive square root of 7. So that's my set builder or solution set notation. Interval notation. Well, this was strictly greater than, so it's going to be a round bracket going from the negative square root of 7 up to positive 1, again a round bracket, unioned with round bracket again because it's strictly greater than the square root of 7 to positive infinity. Any questions? I'm going to have you guys try a couple of your notes. Let's first do x squared. That one's no fun. Let me get a better one here. X squared plus x minus 2 is greater than 4. I'm going to give you a couple minutes to try that. I'm going to pause the recording so you got time to work on it. And we'll go over it in a couple minutes. So for this one, obviously you have to get it equal to 0 or compared to 0, so you subtract the 4. And then we'll treat it as the equation x squared plus x minus 6 equals 0. So that's going to factor to x plus 3 and x minus 2. So we have x plus 3 equals 0, which gives us that x could be negative 3. Or x minus 2 equals 0, giving us that x is 2. So those are the roots we're going to be looking at on the graph. So I've got positive 2, negative 3. So the points I'm going to test, I have 3 regions to test. Let's do a negative 4 is in this region. 0, again, as I go to, is always that, is going to be between them there. And I'll have a positive 3. So let's test x equals negative 4. Again, back in the original inequality. So negative 4 squared plus negative 4 minus 2, is that greater than 4? Negative 4 squared is 16. plus negative 4 minus 2. Well, 16 plus negative 4 minus 2 is 10. That is greater than 4. So we are true out there. Test the 0. Is 0 squared plus 0 minus 2 greater than 4? Well, no. All I have there is negative 2 on the left side. That's not greater than 4. Not true in between there. So let's test x equals 3. That's going to be 3 squared plus 3 minus 2. Is that greater than 4? Well, 3 squared is 9. 9 plus 3 is 12 minus 2 is 10. That is definitely greater than 4. So we are true out here. So our solution set is all values of x such that x is, that was strictly greater than, so we'll go strictly less than negative 3, or x is strictly greater than 2. Or an interval notation, this goes from negative infinity to negative 3. It's strictly less than, so it's a round bracket. Unioned with, from 2 to positive infinity. Again, round bracket because it's strictly greater than. Any questions on that one? Let's look at one more example before we look at our rational example. Let's look at x to the third plus 7x squared minus x minus 5 is less than or equal to 2. I'll give you a couple minutes to try that in your notes, and then we'll go over it. So I realize many of you aren't done, but let's take a look at this here quick. We had to get rid of the 2 on the right side, so we're comparing to 0. Then we use the equation x to the third plus 7x squared minus x minus 7 is less than or is equal to 0 is the equation we're going to be using. And this is 4 terms, so I'm going to do it by grouping. So I change this plus a negative x, so that negative stays with the x. In my first grouping here, I can factor out an x squared, which will leave me with x plus 7. In the second grouping, they're both negative, so I'm going to factor out a negative 1 to make that also x plus 7. Giving me x plus 7 times x squared minus 1. Now you might notice that x squared minus 1 is a difference of perfect squares. So, oops. We're going to leave the x plus 7 for a second. X squared minus 1 factors into x plus 1 times x minus 1. So we have three three zeros here. Nothing potential about them, they are zeros. So x plus 7 equals 0 gives us that x could be negative 7. X plus 1 equals 0 gives us that x is a negative 1. Or x minus 1 equals 0 gives us x is a positive 1. So I have negative 7, negative 1, and positive 1. So I'm going to pick values. Let's do negative 8, probably negative 5, 0, and 2 will be easy values to test. So if I test x equals -8. So we have -8 cubed, get my equation down here, 7x plus 7 times -8 squared minus a -8 minus 7, oops, actually I want to do that as minus 5. Is that greater than or equal to 2? Sorry, less than or equal to 2. Gotta get everything right. So as I test this, -8 cubed is a -512. -8 squared is 64 times 7 is 448. -8 is a +8, and then minus 5. Well, -512 plus 448 is 64, plus 8 is 72, minus 5 is 67. That is not less than 2. It's greater than 2. So we do not have solutions in that region. Let's test the -5 to see if we have any between the -7 and the -1. So -5 to the third plus 7 times -5 squared minus a -5 minus 5. Is that less than or equal to 2? -5 to the third is a -125. -5 squared is 25 times 7 is a +175. Minus a -5 is a +5, and then minus 5. That adds up to 50. That is also not less than 2. Oops, I did something wrong here, didn't I? That's a -64, not a +64, isn't it? So that would be not 72, it'd be a -56. Minus 5 makes that a -61. That is less than 2. I gotta correct myself. The test for -8 was true. -5 is not, so that region is not. You might notice a pattern. The reason I caught that mistake there is if one region is true, the next one adjacent to it is usually false. That's not always the case, but usually. Or if the first one's false, the next one's usually true. I'm going to show you an example here before we're done today where that's not the case, but most of the time that's the way it turns out. Let's test 0. We've got 0 to the third plus 7 times 0 squared minus 0 minus 5. Is that less than or equal to 2? Well, all we have there is -5. -5 is definitely less than or equal to 2, so we are true there. Let's test the 2. 2 to the third plus 7 times 2 squared minus 2 minus 5. So 2 to the third is 8. 2 squared is 4 times 7 is 28. 8 plus 28 minus 2 minus 5 is 29. That is definitely not less than 2. So we're not true over there. So we are good less than the -7 and between the -1 and +1. I'm just going to use the interval notation here. So from -infinity to -7. Now this was less than or equal to in our original. So that means it's going to be a square bracket on the -7. united with from -1 to +1. Again, square brackets because it's or equal to. I mentioned there's a possibility of two adjacent sections both being true or both being false. When does that happen? It happens when one root is repeated. Let's say I have x plus 2 squared as a factor. So that's x squared plus 4x plus 4 is less than 0. Let's do less than or equal to 0, put it that way. Well, that factors as x plus 2 squared, x plus 2 times x plus 2. So that means -2, x equals -2 is my only root. Well, if I test -3 and -1, both of them are going to be false here. Why are they both going to be false? Well, because if I did the function f of x equals x squared plus 4x plus 4, I get a parabola with its vertex right there, and it opens upward. So it's always above the x-axis except at the vertex. Now, if this were strictly less than, there would be no solutions for this. Since it is less than, the only solution here is x equals -2. That's the only time that it is less than or equal to 0. Now, some of these that I've done, we could have used what we know about parabolas and other graphs to work on them. For example, this one here, when I solved it, it was less than or equal to 0. Well, remember we discussed end behavior of a polynomial function. If it is an odd function, the highest power is odd, here it's a 3, and if the coefficient on that variable with the highest power is positive, that's a +1, that means it shoots off to -infinity on the left and up to +infinity on the right. So that's telling us that we should be below 0 here and above 0 over here, which allows us, we could probably just sketch in a graph like that and see from that that we're true here. We're less than 0 here, and we're not true in those two regions. So the graph of that polynomial function can give us the answers. Even more so when it was just a parabola, like this one here. That parabola there, if I graphed f of x equals x squared plus x minus 6, we have the roots, the -3 and the +2, and we know because it's a positive coefficient on the x squared that this parabola opens upward. Where is it greater than 0? Where it's above the x-axis on the two sides. Between those roots, it's below the x-axis, so it's not greater than 0 there. So we can use some of those things, the knowledge of graphing polynomial functions to our advantage. Okay, it is 10:20. Let's take a break here quick, and we'll come back at 10:30, talk about rational inequalities and variation. Is there any sound? Okay, so our next step is we want to look at these rational inequalities. And the rational inequalities work very, very similar to the polynomial inequalities. So if I have a rational inequality, the first step I'm going to do is, again, set it so it's compared to 0. My second step then is going to be slightly different. I'm going to find any roots. I'm going to find those x-intercepts. And I do that by setting the numerator equal to 0. And solving. Second, I find any vertical asymptotes. I do that, if you recall, by setting the denominator equal to 0. And I solve. And then, just like with the polynomials, I test the regions. The roots and the asymptotes divide the x-axis into regions. Just like the roots of the polynomial equations or inequalities. So let's take a look at an example here. And my example is going to be x plus 5 over x minus 2 is greater than 0. So it's already set compared to 0. So I will start out now looking at my numerator, finding any roots. Well, the numerator is x plus 5. If I set that equal to 0, if I solve it, I get a root of x equals negative 5. So there's my root. I'm going to find any vertical asymptotes. I do that by taking my denominator of x minus 2 and set that equal to 0. Solving that for x by adding 2, I get that asymptote of x equals positive 2. So when I look at my graph, my x-axis of my graph, I have a root at negative 5 and a vertical asymptote at 2. Those divide up my graph. So I have the region here. I'm going to have a negative 6. 0 is in here, and positive 3 are the points I'm going to test. Using my original inequality, x plus 5 over x minus 2 is that greater than 0. Let's test the x equals negative 6. So that's going to be negative 6 plus 5 over negative 6 minus 2. Well, that's going to be negative 1 over negative 8. That divides out to be a positive 1/8. That is greater than 0. So we're true out here. Let's test x equals 0. Chances are we're not true here. So we're going to put in, come on, 0 plus 5 over 0 minus 2. That's a positive 5 over a negative 2, which is a negative 2.5. That is not greater than 0. So we are not true between the root and the asymptote. Let's test 3. Now, since this is an asymptote, not a root, there is no predicting. Just because it's not true here doesn't mean it doesn't tell us anything about what's going to happen over there. So let's test x equals 3. That's going to give us 3 plus 5 over 3 minus 2. That's 8 over 1, which is 8. That is greater than 0. So we are true over there. So we have, I'm just going to do the interval notation here now, since I think we've got the solution set notation down. This is from negative infinity to negative 5, unioned with positive 2 to positive infinity. Again, that's strictly greater than, so there is no square brackets, all round brackets. So you can see those aren't too bad to do. And as far as the problems I'm going to have you do, they're not going to be a whole lot more complex than that. The worst they could get would be something like this. X over x minus 1 is greater than 2. It's not compared to 0. So getting it compared to 0 is the difficult part. To do it, I'm going to subtract 2. But now what I have here is x over x minus 1. All minus 2 is greater than 0. Well, I can't work with that. I have to have this as a single fraction in order for my methods of testing this to work. So I have to combine the x over x minus 1 and that negative 2. So the x over x minus 1 is already a fraction. I'm going to make that negative 2 a fraction. Remember, it's a negative 2 over 1, but I'm going to multiply it on top and bottom by x minus 1. So what I get there is negative 2x plus 1 over x minus 1. So I've got the x over x minus 1 plus that negative 2x plus 1 over x minus 1. So I have the same numerators. So my rules of fractions, once I have the common denominator, same denominators I should say, once I have the common denominator, I just add the numerators. X plus negative 2x plus 1, well, x plus negative 2x is a negative x, and nothing to combine with the plus 1, over x minus 1. And that's still being compared to greater than 0. So I try to find roots by using the numerator. Negative x plus 1 equals 0. Well, I subtract 1 from both sides. Negative x equals negative 1. And I divide by negative 1 to get rid of the negative on the x. Gives me x equals 1. So that's a root. I do the same on bottom. X minus 1 equals 0. That also gives me x equals 1. That is an asymptote. So this only divides my graph into two regions. Both of my critical points here are at 1. So I'm either less than 1 or greater than 1, strictly. So let's test. Let's test 0, and then we'll test 2. So if I test 0 in here, going back to my original inequality, 0 over 0 minus 1, is that greater than 2? Well, 0 minus 1 is negative 1, so 0 over negative 1 is 0. That is not greater than 2, so that doesn't work. Let's test 2. 2 over 2 minus 1. That's 2 over 1. That equals 2. That is also not greater than 2. So there are no solutions to this one. There are no points where this graph is greater than 2. Realistically, why is that so? If I take what I got here, when I simplified this, that negative x plus 1 over x minus 1, negative x plus 1 can be thought of as a negative 1 times x minus 1 over x minus 1. You can see the x minus 1's factor out. This is just negative 1 greater than 0. That's never true. Let's do one more example, one that maybe actually works out. Let's do 1 over x minus 3 is less than 1. So now we have to subtract 1 from both sides. So I have 1 over x minus 3 minus 1 is less than 0. I need a common denominator. So I'm going to take that negative 1 over 1. I'm going to multiply by x minus 3 on top and bottom. So what that gives me, I have 1 over x plus, or x minus 3 there yet. Here I have negative x plus 3 over x minus 3. And of course, that's still less than 0. I can combine here. I have the same denominators. So it's going to be x minus 3 in my denominator. 1 plus negative x plus 3 is negative x plus 4. I combine the 1 with the 3 to make 4. Less than 0. So I find my roots. That's where negative x plus 4 equals 0. If I subtract 4 and divide by negative 1, that gives me x equals 4. I find my asymptotes. I said x minus 3 equals 0. Well, pretty easy to see there. That's where x equals 3. So looking at a graph, I have a root at 4 and an asymptote at 3, dividing me into 3 regions. I'll use 0 again since it's easy. Here I've got to use like 3.5, and over here I'll use 5. So if I test 0, negative 0 plus 3 over 0 minus 3, that's just 3 over negative 3, which is 1. Is that less, or negative 1? That is less than 0. So we're true over here. Test the 3.5. Well, negative 3.5 plus 3 over 3.5 minus 3. Well, this is a negative 3.5 plus 3 is a negative 1/2. 3.5 minus 3 is a positive 1/2. That's a negative 1. That is still less than 0. We're true in there as well. Let's test, oops, I circled a little large there. We're true between 3 and 4 there. Let's test the 5. Negative 5 plus 3 over 5 minus 3. Negative 5 plus 3 is a negative 2. 5 minus 3 is 2. That's negative 1 as well. We appear to be true out there. What does that mean? Well, that means that this graph has some sort of shape like this. It's always less than 0 except at the asymptote. It doesn't have a value, and the root, it's equal to 0. So interval notation here, we go from negative infinity up to that asymptote of 3, united with from 3 to 4. Again, 4, it's equal to 0, and this is strictly greater than, united with 4 to positive infinity. Okay, so enough on the inequalities. We're going to shift gears here a little bit, moving on in chapter 3, section 3.7. We're going to talk about variation. Variation is a big concept in my world. I've done some work in engineering, and variation talks about the relationship between 2 or more variables. It's usually the most useful in practice when we can get it down to just two variables and everything else can be held constant. But we'll look a little bit at some relationships between more than two variables, three or more. There are two types of variation. Direct variation, so one we'll talk about first. And in direct variation, let's just say we've got values x and y. If the value of x gets larger, the value of y has to get larger in a proportional amount. Or similarly, if x gets smaller, y also gets smaller in a proportional amount. Direct variation is considered to be a constant ratio. When we say directly proportional to, that's what we're applying here is a constant ratio. It's a proportion. So the ratio of y over x is always a constant. Now there's a little bit more useful version of that equation. Instead of saying y over x equals a constant, we often look at it as y is equal to a constant times x. Notice I just multiplied both sides by x. So if I'm giving an example, and I say that y varies directly as x, what that means is that this is of the form y is equal to a constant times x. If I say y varies directly with x and y is 42 when x is 14. Now we have even more information. Y varies directly with x gives us that generic form, y equals constant times x, kx. This second piece, however, allows us to find that constant k. Y is 42, so I put 42 in for y, when x is 14, so I'm solving for that constant. I divide by 14. 42 divided by 14 is 3 equals k. Well, we can take it another step further. Y varies directly as x if y is 28 when x is 4, find y when x is 9. Now there's a third piece of information here. So we're given the relationship, y varies directly with x, y equals constant times x. We're given, this is what's referred to often as a known condition or an initial condition. Y is 28 when x is 4. So I put 28 in for y and 4 for x, and I solve, dividing by 4, I get 7 equals k. So that tells me that this relationship, y equals kx, is actually y equals 7 times x. And now we have the question being asked, or trying to extend it to another value. Find y when x is 9. Well, now I can just put 9 into that equation for x. 7 times 9 gives me that y is 63. Well, that's pretty straightforward, and it doesn't always stay that simple and clear. We can have y varies directly as the square of x. If y is 45 when x is 3, now I'm going to ask this a little bit different. Instead of find y, I'm going to say find x when y is 20. So right up here, slightly different. Y varies directly. That still means y equals a constant times something as the square of x. So it's not just the constant times x, it's the constant times x squared. Now we still have our known condition here. Y is 45, put 45 in for y, when x is 3. So I put 3 in there for x. Now we have a little calculation to do before we can find our constant. We've got to do the 3 squared. 3 squared is 9. Then we'll go ahead and divide. We divide by 9 to get 5 equals k. So our equation is y equals 5 times x squared. And this next part I did a little differently as well. Instead of giving you x, I gave you y. Find x when y is 20. So I'll put 20 in there for y, and I'm looking for x. I've got to divide by 5 to get 4 equals x squared. Then we square root. 2 equals x. Now the question is, could it be a negative 2? Yes, it could. Inverse variation works the opposite direction. In inverse variation, if the value of x gets larger, the value of y has to get smaller in a proportional amount. Or the other way around, if x gets smaller, y has to get larger. Inverse variation is not a constant ratio, it is a constant product. So it takes the form of x times y equals a constant. Again, often more useful if we solve it for y to get that y equals a constant divided by x. So if we are told y varies inversely as x, what that's telling us is y equals a constant divided by x. Now, of course, we can have more information just like with direct variation. So I'm just going to add the next 2 steps all at once here. Y varies inversely with x if y is 8 when x is 6. Find y when x is 2. Now we know that x got smaller, we know y is going to have to get bigger because of the relationship. Let's go through the steps. Y varies inversely with x. That's telling us that y equals a constant divided by x. We have our known condition. Y is 8 when x is 6. We solve to find the constant. Multiply by 6. 48 equals our constant. So that tells us that formula is really y equals 48 over x. And now finally, they're asking us to extend this. Find y when x equals 2. So I put 2 in there for x. 48 divided by 2 is 24. Y equals 24 when x equals 2. So if I tell you y varies inversely with the cube of x, if y is 5 when x is 2, let's see, is that going to work? Yeah, it'll work. Find y when x is 3. It'll give us an ugly number, but who cares? The y varies directly with, or inversely, I should say, with the cube of x. So y equals a constant divided by something. Well, it's not divided by x, it's divided by x cubed. We have a known condition here. Y is 5 when x is 2. So 5 equals k over 2 cubed. Well, 2 cubed is 8. We multiply by 8 to get that 40 equals our constant. So that relationship was really y equals 40 over x cubed. Then it asks us to find y when x is 3. So I put 3 cubed in there. That's 40 over 3 cubed is 27. So y is equal to 1 and 13/27. Any questions? Some examples of where this would get used, or any of these would get used. Well, let's talk about dosage calculations. A 40-pound patient requires 24 milligrams of medication. How much would a 70-pound patient need? So the first question you have to ask, is this direct or is it inverse? If the weight of the patient goes up, do you expect the dosage to go up or to go down? Up, yeah, expect them both to go up. This is direct. If the weight goes up, you expect the dosage to go up. So that's telling us y equals a constant times x, because it's directly related. Well, we put in our values here. So that part wasn't explicitly told to us. We had to get that from the problem, within the problem itself, of whether it was directly or inversely related. Now that it goes into the initial or the known condition, 40-pound patient is 24 milligrams of medication. I'm going to let y be the medication, x be the pounds of the patient. So 24 milligrams equals a constant times 40. I divide by 40, I get 0.6 equals my constant. So y equals 0.6 times x. Now there's units on that. That's actually 0.6 milligrams per pound is technically what that's saying, but we're ignoring the units right now. And how much would a 70-pound patient require? Well, we put 70 in for X. 0.6 times 70 is 42. So we would expect that 70-pound patient to require 42 milligrams of medication. A gas is at 24 psi when contained in 12 cubic inches. Find the pressure if the gas is confined to 4 cubic inches. So what this is saying is we have a gas. What gas it is, we don't know, but it's contained in a certain volume, currently 12 cubic inches. If we squeeze that volume down to 4 cubic inches, do we expect the pressure to get lower or higher? We'd expect more pressure. So when one got smaller, the other got larger. That is an inverse relationship. So rather than X and Y, I am going to use P for pressure and V for volume. So the pressure is equal to a constant divided by the volume. Now we were given 24 psi when it's 12 cubic inches. So 24 equals a constant divided by 12. We solve that by multiplying by 12 on both sides. We get 288 equals our constant. So this equation is really that the pressure equals 288 divided by the volume. Brass, what's the pressure when it's confined to 4 cubic inches? So put that as 288 over 4 is 72 cubic inches. Any questions? Well, sometimes, as we said, you have more than 2 variables. In most cases in life, in order to get a situation down to 2 variables, you have to artificially constrain many of the other variables. You have to force them to stay the same. In science, we do this all the time. We like to get all of our experience down to just 1 variable or 2 variables that we're comparing to each other, which allows us to, forces us to have very strict controls on everything else to keep them constant. Just like up above here with this pressure and volume one, you'd have to make sure the temperature stayed the same. If that temperature didn't change, then this relationship doesn't hold. When we're looking at more than 2 variables, we cannot have 3 variables that all have the same relationship with each other. Let's say I've got X, Y, and Z. There is no relationship that allows all 3 of them to get bigger together. What do I mean? Well, there's no equation I can put them in where all 3 of them can get larger. So usually what we have is something called combined or joint variation. And in combined variation, 2 of the variables interact directly with each other. One of those variables will still interact directly with the 3rd variable, but that 2nd and 3rd variable have to react inversely with each other. A great example of this, well, first of all, let's do the equation. The typical equation that was used for this is that y equals a constant times x and times z. So here y varies directly with x and it varies directly with z. If X gets larger, Y will tend to get larger. If Z gets larger, Y will tend to get larger again. But X and Z vary inversely with each other. If Y doesn't change, if X gets bigger, Z has to get smaller, and the other way around. A great example of this is electricity. Ohm's law in electricity tells us the voltage over a resistor is equal to the current through that resistor times the resistance of the resistor. So normally what we look at here is one thing being held constant over the other. Let's say the resistance is held constant at 200 ohms. That little symbol that looks like kind of an upside down horseshoe is the symbol for ohms. You don't really need to know that. So at 200 ohms, if we have a current of 2 amps, gives us a voltage of 400 volts. We would get that, we can test out our equation here by plugging those in. 400 equals 2 times 200. You can see that equals out. So what we normally do in this type of relationship is we'll specify the variable that doesn't change. If resistance remains constant, a current of 3 amps gives 18 volts. Find the voltage created by a current of 8 amps. So in this case, the resistance becomes our constant. V equals IR. We are given an initial condition or a known condition where we have the current is 3, and the voltage is 18. So we can solve for R. Dividing by 3 there gives us that resistance has to be 6 units. So this relationship is the voltage is equal to the current times 6. So it asks find the voltage when the current is 8. That's just 8 times 6, where the voltage is 48. So in that case, when the resistance was held the same, the voltage reacted directly with the current. If voltage is held constant, three amps of current, sorry, I should do the other way. I'd say that 24 ohms gives 3 amps of current. Find the current at, let's say that resistance goes to 8 ohms. So again, voltage equals current times resistance. We're given that initial condition. 3 amps and 24 ohms gives the voltage. We just multiply those up to get 72 is the voltage. So this relationship here becomes 72 equals current times resistance. Find the current if the resistance is lowered to 8. So we put 8 in for R, and we can divide. So 9 is the current if the resistance is lowered to 8 ohms. This variation is extremely powerful tool. I used it a lot in engineering work. When you don't know the actual formula for something, but you do know certain conditions that exist. Now here we use just a single known condition. It's generally best if you have 2 known conditions. That way you can use one to find the constant and use the second one to test it, because sometimes it's not just y equals kx. Sometimes there's some little factor out there. So you can use it to actually find the formula and apply it to other conditions as they arise. Okay, with that, that's all of our material for today. So there is new homework. This is homework, was it 6A, I believe? It'll be due next Tuesday. That way you got time to ask questions in class next week if you want to. There is no quiz due this Friday. This will be, the Friday after a test is the only time we don't have a quiz due. But you can remember to work on those test corrections. Any of the problems you have wrong, redo them, showing all your work, probably on another sheet of paper, scan them and send them to me. For those of you that weren't here right at the very beginning, there were 2 questions on the test that I decided weren't fair. I'm not going to tell you what they are because some of you had them correct and I'm not going to take those points away from you. But what I did is, you saw in the grade book, there's a test 1 correction. I just put 7 points in there for everybody, so that adds 7 points to your scores. Now, with that said, you can still do corrections and get points back, even on the ones that I decided weren't fair. They are still answerable. They have correct answers. But I decided they were too difficult really to ask on a limited time test like that. Those test corrections, I will give you 2 weeks to get those done. So 2 weeks from today. At some point next week, if you have questions on those, I will answer those for you briefly. Okay, if there are no questions, you guys have a great week and we'll see you next Monday.